In this video, we're gonna find the matrix for this linear mapping. Okay, to prove that this one is a linear mapping, we have to prove that f of alpha x plus beta y is alpha f of x plus beta f of y. It's clear, but I think I'm gonna do a separate video for that one with alpha and beta real numbers, and x has x1, x2, x3, and y has y1, y2, y3. Okay, now our aim is to find the matrix. There are many ways to find the matrix, but since we are trying to find the matrix in the standard basis for R3, which we know is let me use this pen, which E1 has 1, 0, 0 as coordinate, E2 has 0, 1, 0, and E3 has 0, 0, 1. So we need to find the image of each of these vectors by our mapping F, and we can represent them in columns. And doing that, that's the matrix of this linear mapping. Okay, let's do that. So first, f of E1. Okay, so what we do is for x we plug 1, for y we plug 0, for z we plug 0 in here. So what we get 1 minus 0 is 1, 1 plus 0 plus 0 is 1, 1 plus 0 is 1. So f of E1 is 1, 1, 1. F of E2, okay, so for x we plug 0, for y we plug 1, and for z we plug 0. So we have minus 1, 1, and 1. F of E3, so x is gonna be 0, y is gonna be 0, and z is gonna be 1. So we have 0, 1, 0. So to get the matrix, we just let's call it A. Okay. So we represent these vectors in columns. So f of E1. So let's write it here. F of E1, f of E2, f of E3. Okay. So this one is going to be in columns 1, 1, 1, minus 1, 1, 1, 0, 1, 1. And here we will have E1, E2, E3. Okay, I'm just writing this one. You don't see them, but I'm doing them for the explanation. So the matrix of this linear mapping is this one: 1, 1, 1, minus 1, 1, 1, 0, 0, no, sorry, 0, 1, 0. There is no one here because it's this one here. So I made a mistake. So this is the linear mapping for this. So this is the matrix for this linear mapping. Okay. A quick way to check is you multiply this one. So you multiply this one by the column x, y, z to see if you get this one. Okay. So what we're gonna do is, if that's what you see in the books, f of x is a times x. Okay. A is the matrix, and x, big X, sorry, it's a big X. So big X is x1, x2, x3. But for us, we used x, y, z. Okay. When we have more numbers, we're going to use 1, 2, 3, 4, the index by the numbers. But when we have a small matrix, we're just going to use x, y, z, or t. Okay. So let's check when we multiply A, if we get this one, the original mapping. So let's do that. 1, 1, 1, minus 1, 1, 0, 1, 0. We're going to multiply this one by x, y, z. Okay. How we do the multiplication? Okay. So this is this matrix, a 3 by 3 times 3 by 1. So we're going to get 3 by 1. Okay. Okay. So that means 3 rows, 1 column. That's the representation of a vector. But we can do it in rows as well. Okay. Okay, but anyways, let's do the multiplication. How do we do multiplication? We multiply this row by this column, component wise. That means 1 times x plus minus 1 times y plus 0 times z. We get x minus y. Next, we multiply 1 times x plus 1 times y plus 1 times z. We get x plus y plus z. Okay, and finally we get 1 times x plus 1 times y plus 0 times z, which is x plus y. So this mapping here is written in row form. Here I wrote it in column form. It's the same thing. So this is a 3 by 1. It's a vector. 3 rows, 1 column. Okay? So it's the same thing. So we have gotten the same thing that we started with. So that means the matrix is right. So we did great, and we get the matrix of this linear mapping. I will prove the next part, this property, because it seems to me it's challenging to some of the, so you need to get used to this. I'll do one more.